This is Lecture 5, Dynamic Inconsistency and Credibility in Monetary Policy. Over the next few weeks, we're going to look at monetary policy in more detail, specifically how different types of monetary policy affect the macroeconomic economy, specifically in terms of output and inflation. One of the questions we'll ask is, does pegging the exchange rate of a high inflation economy to a low inflation economy give us a better macroeconomic outcome, i.e. lower inflation? And if the answer is yes to that, then there's two reasons why we should adopt a pegged exchange rate. One being that the exchange rate is less volatile, and the other is that we have better macroeconomic performance in terms of lower inflation. Today we're going to look at two types of policy: policy under discretion and policy under commitment. What do we mean by monetary policy under discretion? The monetary authority reacts to the economic conditions in each period and uses its discretion so that the public are unaware of the policy in advance. To define this specifically as an environment where monetary policy is set after the public have formed expectations. So the order is that the public form expectations first, then the policymakers choose the actual rate of inflation, or that's the optimal rate of inflation, according to the loss function, and then the difference between expected and actual inflation determines output in the economy. Now suppose that output is determined by the supply function. Output supplied is equal to its natural rate, the long run rate of output, plus some deviation from the natural rate caused by an inflation surprise, which is the difference between inflation and expected inflation. And output may also be negatively affected by supply shocks. And here we set these shocks as exogenously determined and with zero mean. Also, the steady state, we know that inflation will be equal to its expected inflation. So when y is equal to y bar, inflation must be equal to expected inflation. And also that when inflation is equal to expected inflation, that y must be equal to y bar. So these are our steady state values for output and inflation. Now the government minimises a loss function, which is that the loss to society, L, is equal to half the output gap squared, and the output gap being the difference between output and target rate of output, plus half of lambda times the inflation gap squared, where the inflation gap is the difference between actual inflation and target inflation. There is a weight here also on this element of the loss function, lambda. The lambda represents the amount that the central bank or government cares about inflation, or the inflation gap, over and above that of the output gap. And notice that the loss function is increasing in the deviations of output and inflation from their target rates. So volatility in the economy causes greater losses for society. Now we can substitute the supply function, to think of as a constraint, into the policymaker's loss function. So the loss function now takes account of the constraint presented by the aggregate supply relation. So we can substitute equation 1 here into equation 2. And the best place for that is here on where we have y on the first term on the right hand side. Replace y with the right hand side of the aggregate supply equation, because y is equal to y here. So substituting, we have that loss is equal to half times y bar plus pi minus pi e minus v, which is y, it's here, minus y tilde, which comes from here, all squared, plus half of lambda times pi minus pi tilde all squared. Now we can set pi tilde, or the target rate, pi equal to 0, and we can introduce a new variable, which is k. And k is the amount that the policymaker wants to keep output above its natural rate, and we assume that this is greater than 0. So that y bar minus y tilde becomes minus k. Now we can write the loss function L is equal to half times pi minus pi e minus v minus k all squared plus half of lambda pi squared. Now we can optimize or minimize the losses by differentiating the loss function with the constraint given by the aggregate supply relation built in with respect to inflation. But dl d pi is equal to inflation minus expected inflation minus v minus k, essentially the square around this term, and the half have cancelled out from the differentiation, and plus pi times lambda. Before this was half lambda pi squared, differentiating with respect to pi gives us just pi lambda, and we set that equal to 0. So that's the first order condition where losses are minimized. Rearranging equation 4 gives us equation 5. So we leave pi, the two terms in pi on the left hand side, and bring everything else onto the right hand side and solve for pi. We have optimal inflation, which is equal to k times expected inflation plus v, all divided by 1 plus lambda. Further, we can find optimal output by substituting our optimal inflation rate into the aggregate supply equation, just as we have done with rational expectations solutions, finding optimal output from the optimal price using the aggregate supply relation. We do that here. We get optimal output as equal to y bar, that's the natural rate, plus the deviations, k minus lambda pi e minus lambda v, all over 1 plus lambda. The equations given in the previous slide, equations 5 and 6, are the policymaker's choice of inflation and output given the economy's loss function. Notice that they depend on the supply shock, and also that they depend explicitly on the rational expectation formed by the public. Remember that the public have to form expectations of inflation first, and with discretion. So with complete knowledge of the model, the rational agent will choose the optimal rate of inflation as the expected rate. So that pi e is equal to the expected value of the optimal inflation rate, which is k plus pi e divided by 1 plus lambda. The shock v is 0 here because the expectation of the shock is 0. We can solve for pi e to get that the rational expectation of inflation is equal to k divided by lambda. K being the amount that the policymaker wants to keep output above its natural rate, and lambda being the weight that the policymaker puts on the control of inflation. Now we can find the optimal rates with the rational expectations rate of inflation. So we substitute equation 8 into equation 5, which is optimal inflation, and equation 6 for optimal output. We have that optimal inflation is now equal to k over lambda plus v divided by 1 plus lambda, and optimal output is equal to y bar, the natural rate, minus lambda v divided by 1 plus lambda. If we differentiate the optimal rates with respect to the supply shock, in other words, take d pi dv and dy dv, we can see how inflation and output react to the supply shock. So d pi dv is equal to 1 over 1 plus lambda, and dy dv is equal to minus lambda over 1 plus lambda. So under discretion, we see that policy, this is lambda, stabilizes inflation and output. So higher values of lambda will make a smaller reaction of inflation to the supply shock, and that is intuitive in the respect that it was lambda, the weight that the policymaker puts on inflation in the loss function. Also, that output stabilization is greater for smaller values of lambda, which again is intuitive. Let's discuss the solutions for optimal inflation and optimal output. We have that optimal inflation is equal to k over lambda plus v over 1 plus lambda, and for optimal output is y bar minus lambda v over 1 plus lambda. And notice that in the case of v equal to 0, in other words, on average, that there will be no real effect. What output will be around its natural rate, and inflation will be positive. And this is the neutrality result that we got from lecture 2 under the solution to the rational expectations model. So the implication, the assumption of rational expectation, the public knows, has full information and knows all the variables and outcomes of the model. So thus, the agent is going to assume that the solution is the inflation rate and will set its expectations accordingly, and that in turn will ensure that inflation is positive. So by setting the rational expectation of inflation to k over lambda, the economy settles on its natural level of output with a positive rate of inflation. Now we can calculate the value of the expected loss under discretion by using equations 9 and 10, our solutions, and putting them into the loss function, equation 2. And we're replacing output in the loss function by optimal y under rational expectations and optimal pi under rational expectations. If we do that and take expectations, we have the expected loss under discretion is equal to half times 1 plus lambda over lambda times k squared plus lambda over 1 plus lambda times the variance of the supply shock. We'll revisit that at the end of the next section to compare the expected losses, one under discretion and one under commitment. We now look at monetary policy under commitment. How do we define commitment? Well, the policymaker sets the monetary rule in advance before the public form expectations about inflation. So there's some commitment by the policymaker. And any particular rule, one we have got here, is that inflation pi is going to be some target rate, and we call this phi tilde, plus some reaction to the supply shock, phi being the parameter on the supply shock V. And phi tilde and phi are constant coefficients. If phi is greater than 0, that's the monetary policy rule is a contingent rule. In other words, it can react to a supply shock. It may be that the policymaker does not want to react to any supply shocks and strictly wants to control inflation. However, there is some contingency here. If phi is equal to 0, we just have a fixed or simple rule where there is no contingency for supply shocks. So we've just said, on the simple rule, an example of a simple rule being inflation is equal to 2%. Here, pi is equal to phi tilde, and there's no stabilization and there's no reaction to the shocks. We gave an example of a fixed rule in lecture 3, which was the money supply growth rule. But we could also think of a rule, a fixed rule, as a fixing of the exchange rate. The optimal values of phi tilde and phi can be computed by first finding the inflationary expectations as a function of phi tilde and phi, and then optimizing these parameters according to expectations. So the assumption is that the commitment by the central bank to the fixed rule is credible, i.e. the bank will stick to its rule. That is the major assumption here, and on that basis the public form expectations assuming the bank will stick to its rules. So we have that the inflation of expectation is going to be set according to the monetary rule that we have, which is the expectation of phi tilde is just phi tilde, and the expectation of phi v is phi times E of v, which is 0. So the public form expectations around the target rate, phi tilde. We start with the aggregate supply relation, y is equal to y bar plus pi minus pi e minus v. And we substitute into the aggregate supply equation our monetary rule, which is equation 16, and our solution for the expectation of inflation, which is equation 17. So we replace pi with the monetary rule here, and replace pi e with the expectation, or the rational expectation of inflation, which we know is the target rate. When we simplify this, we have a phi here and a minus phi. It simplifies so that y will be equal to y bar plus phi v minus v. Now we can take our adapted aggregate supply equation, equation 18, and our monetary rule, equation 16, and put those into the loss function. Remember, our loss function was L is equal to half times y minus y tilde. This becomes L minus 1 half times phi v minus k, where the k comes from y tilde minus y bar, plus half times lambda times pi squared. But here we've replaced pi with the monetary rule, phi tilde plus phi v. We take expectations of equation 19, we have the expected loss is equal to half of the expectation of phi v minus k all squared plus lambda phi tilde plus phi v all squared. To find the optimal values of phi tilde and phi, we can differentiate the expected loss function with respect to phi tilde and phi. So dl d phi tilde is equal to lambda times the expectation of phi tilde plus phi v. You know the expectation of phi v is equal to 0, so we just have phi tilde is equal to 0. So the optimal fixed inflation target rate is 0%. Differentiate with respect to phi, the dl d phi is equal to the expectation of lambda phi tilde v lambda phi v squared plus phi v squared minus v squared minus kv, setting that to equal to 0, implies that phi must be equal to 1 over 1 plus lambda. Those are our optimal values for phi tilde and phi. Now that we finally have our optimal values of the policy parameters, we can put the policy parameters into the monetary policy rule to get optimal inflation, and then we can use the AS with equation 18, which is the rational expectation of inflation, to get optimal output. Doing that, we get that optimal inflation is equal to V over 1 plus lambda, and optimal output is equal to y bar minus lambda V divided by 1 plus lambda. So under commitment, and in the absence of shocks, we see that the inflation rate, optimal inflation rate, will be equal to 0, and optimal output will equal to y bar. Notice the difference between the case of commitment and discretion. So we can also take the reactions of the optimal rates to the shocks. So we take d pi dv and dy dv. You see that d pi dv is equal to 1 over 1 plus lambda, and dy dv is equal to minus lambda over 1 plus lambda. So under commitment to a contingent rule, monetary policy stabilizes to the same extent as in our case of under discretion. If you compare these with the discretion results, you'll see that the reaction of the optimal rates to changes in the shocks is the same. Now that we've calculated the optimal rates under discretion and under commitment, we can compare these rates. Let's look at the case for inflation. The difference between the optimal rate for discretion and optimal rate for commitment is equal to k over lambda. The difference of the output rate for discretion, the output rate for commitment, is 0, so they are essentially the same. So under discretion, there is higher inflation than under commitment, so there is some cost to using discretion, but it's only a cost in terms of inflation. In terms of output, there is no cost between commitment and discretion. Something we call the inflation bias is the bias that comes from allowing policy makers to choose policy after agents have formed expectations. This inflation bias depends on k and lambda. We know that k is the amount at which policymakers like to keep output above its natural rate, and lambda is the weight that policymakers have put onto the control of inflation or stability of prices. So a low k gives us a lower inflation bias, and a high lambda, which is intuitive. Policymakers have one objective, mainly inflation, then it's going to obviously eliminate the inflation bias. Now we can look at the expected losses under commitment and discretion, and notice that under discretion the loss to society is greater, and we can see that difference quite clearly by just looking at the two rates. Here we have 1 in front of k squared, but here we have 1 plus lambda over lambda, which is the number greater than 1. So the expected loss under discretion is greater than under commitment. So in other words, commitment produces superior macro outcomes. You could say that it's better for policymakers to tie their hands. But what happens if policymakers decide to cheat? So there is an incentive for the policymaker to cheat. The policymaker can announce and commit to a rule. The agents form their expectations based upon the rule, and then the central bank cheats or reneges on the commitment. One way to get around this is to introduce independent central banks, something we call an independent institution, that can try to enforce the rule. The trouble is, detection relies on the fact that in reality our agents don't have full information. So there is incomplete information. But one way to try to enforce credibility or to maintain credibility is to put in some kind of commitment technology. And one example of that is a pegged exchange rate. And we discuss this case next week. So we have commitment with a commitment technology.